everybody gets so uppity about the whole country when the leader is a nutcase, because we've had them too. We've had some nutty leadership. Maybe not as bad, but whatever, I'm just saying. I don't like it when Americans get all uppity about Iran as a country, because every Iranian I've ever met is super rad. And separately, when I hear a lot of people wanting to launch military action against Iran, I kind of feel like maybe they know something I don't, or this is not a big deal. Because 3% 235 is a long stretch from 90% 235. That's weapons grade. Anybody want to talk to me about enrichment?
No, I said you have your button up there.
I have my button. I don't know which button.
The button on the wall.
Oh, yes, right. Do not enter Iran. Because I kind of feel like, man, a lot of our military intervention is counterproductive sometimes. I don't like to see all of you getting shipped off to be somebody else's target practice. Okay. Enrichment is underlined as a vocab term. It is when you take 235 from 0.72%, relatively speaking, up to 3%. What you've done is actually make this more common by removing that stuff in enrichment. Once we have fuel-grade uranium, we make it into these little pellets that are about the size of a lemon head. Anybody seen like lemon heads, the little yellow candies you get on the spot? So good. It's like pure sugar and like, I don't know what else that is. MSG maybe? Yeah, something. Yeah, that's so good. Okay. Watch. Fuel grade. I'm not the thing we were just thinking about. Fuel grade uranium is made in these little pellets, and then follow with me. We take those pellets and we pile them up in these little tubes, and we seal the tubes, and we put those tubes in these little racks, and then we screw those in, and then we take a rack of tubes and we stack it into these big racks, and that is a reactor core, a fuel assembly. Anybody want to talk to me before we get to the nuclear chemistry for a moment? We have enriched uranium. We've put it in the reactor. Now we've got to talk about what happens in the reactor in terms of chemistry. Anyone? Really?
So the reason why 238, why would 238 be more common? Like, wouldn't it take more energy?
Bro, quit asking me. The baby Jesus said so. I don't know why any isotope distribution is such. I am convinced that there are fields of chemistry that study the forces of each element's atoms, and they do have different attractive and repulsive properties.
Yeah, and it tends to be like quantum mechanics, sort of like stuff that's really counterintuitive. A lot of
and so there's some really counterintuitive stuff. For example, 235 is pretty stable, and 238 is pretty stable, but 236 is impossible.
Yeah.
So let's do this. I've been talking about rocks and powders, but now I'd like to talk about one atom for this reaction. Remember that this is one atom inside the pellet, which is inside the tube, which is inside the rack, which is inside the tower, which is inside the fuel assembly. Everybody follow me on all that?
Those are the fuel rods.
So I'm going to go down into the pellet, and then inside the pellet, there's like a gajillion atoms. One atom right there. 235 is stable. I don't know if you'd want to like eat it, but I think it's definitely stable. It has a half-life of like 2.5 billion years. That's relatively stable. You take uranium, 235. And this is not a simple process. I have no idea what kind of leprechauns and voodoo magic are required to throw a neutron. But you just, grab one off the shelf and throw it at the atom. Okay, fine. And once you have, that becomes heavier, 236, because it's got one extra piece now. And this asterisk, you should know, that means it's unstable. That will last on our planet some extremely small fraction of a second. I would say hundreds or even thousandths of a second. When you throw the neutron at it, it just goes, oh, oh, oh. That's what happens. Just like that. Oh, oh, oh. Now, I'll tell you a little story. My little dude, Toby, you guys know I have a really beautiful son named Tobias. My little dude, Toby, wanted to, he likes being helpful around the house. He's just about to turn 3. So if he's not like breaking things or eating them, he wants to help. And my wife says, hey, do you want to have a fire tonight? And I'm like, sure. So I walk outside and I start grabbing some firewood. And I say, hey, Toby, what are you doing? He's like, I want firewood. I'm like, all right, dude. So I put a couple sticks on it. And usually he can only carry like 2 sticks. But I already had all the big stuff, and I needed some more little sticks to like put at the bottom of the fire so it's still cold. So I started putting sticks on it, and he's like, more, daddy, more, daddy. And I was like, bro, I don't know, man. And I was like, you sure? Is that enough? He's like, no, I want more. And I looked down, and like, proportionately, it would be like me having like a pile like this. I mean, he's like that tall. So his little pile was actually like getting pretty respectable. And I was like, dude, I don't know. I think you're going to blow it. This is kind of a lot. He's like, no, I want more. I was like, all right, man, here you go. And he's like, uh-oh. And he's like, and I was like, is this going to work out, man? And he's like, yeah. And he's like, one step, he goes, hey, Pop, oh, and he starts to drive before it happens. He's like, oh, I knew it was good. So anyway, he's like destabilized. Too many pieces can't hold together. This is what I mean about those quantum forces that hold together an atom that's totally over my head. I don't get it. 235 is relatively stable. 238, for some reason, is stable. But in the middle there, 236 is extremely unstable. The only reason that we build it is because we know it'll break. And when it does break, we get that glorious release of energy. So look at me. It's called nuclear fission. It is the pow kaboom where 236 has broken. And literally, the nucleus of that atom splits. And as all those pieces reorganize, you release a lot of extra energy. What used to hold all the pieces together that now doesn't have to hold them together, that's apparently like some astronomical amount of energy. And again, this is counterintuitive, that something so small we cannot see releases more energy than anything we could see. But it takes a lot of energy, I guess, to hold the atoms together.
Once you break that lattice, there's all that energy.
So apparently he gets it, but it does blow my mind. Okay. Now look up here, because I'm going to start spewing a bunch of little details at you. The most common fission products, it's also called radioactive decay products. It's also called spent fuel or high-level radioactive waste. A lot of names, you can kill with underlying stuff. I'll get back to that. The most common ones are molybdenum-103 with an asterisk and tin-131 with an asterisk. I'll explain those in a second. But also you get a couple of neutrons and energy. And when I say energy, I mean a lot of energy, like astronomical, unbelievable volumes of energy. I want everybody to notice that in this conversation, the one critical detail, like the heads-up thing that everybody has to know, is the neutrons. Because don't forget, they got the party started, and we were just talking about one atom, but there's others. So when the initial spark gives you more sparks, you know you're going to head into what's called a chain reaction. We'll come back to that. Well, let's talk about the radioactive decay products, okay? First of all, what does the word radioactivity mean? What is radioactivity? Right, when atoms give off particles, that's radioactivity. If you don't know that, write it down. Radioactivity is when pieces fall off an atom. And you can imagine, if you have a whole lot of extra pieces, please look up, like the largest element that lives on Earth. If you have a whole lot of pieces, then you've got a lot of spares to give off. What? Like the neutron, proton, and electron, the things that make up the atom. Yeah, subatomic particles. Now, I'm going to drop another Lego analogy on you. Because as you know, I like Legos. Every time I would build a Lego castle, remember I got a castle set when I won my gift certificate. Did I tell you the story? Oh man, I came to the United States and I found Kool-Aid thing on the ground, and like we didn't have a lot of toys because my family was a bunch of nerds and we were like fresh off the boat with like $0 American dollars. So like I didn't have a lot of toys, and I was walking with my. Did I tell you that I had very few friends in elementary school when I first came to the United States? Yeah. So I was talking with my homie Peter, my Hungarian friend. And we're like walking down the sidewalk, and I found Kool-Aid, and I was like, sweet, I love Kool-Aid. And I grabbed the packet, and it was empty. And I was like, oh, it's empty. And when I went to go throw it away, he's like, oh, dude, look, on the back. And I was like, I don't understand what this says. And so we like had to like explain everything in like pantomime because we didn't really communicate. And so he told me, look, you like fill this out, and then you mail it away, and then they have like a drawing, and if that is your name, then they send you money. And all I heard was, wait, they sent me money? So I just like sent it off, and I won, and I got a $100 gift certificate to Toys R Us. And back in 1985, going to Toys R Us with $100 was like, oh! And Legos used to be way cheaper, so I bought like 3 big sets of Legos. And I was like king of the block for a couple days, and life was really good. Yeah, and then it went back to me. So anyway, I love Legos, and by the way, they had just started to come out with like the kits that were like themed, and one of the first themes they came out with were castles. So I used to build castles with my Legos. And one thing I remember is every time I would build a Lego castle, when I broke it on purpose or it broke by accident, it had like structural weaknesses. Like the towers weren't very well attached to the body, and then the little piece right over the drawbridge would always break. Okay, structural weaknesses. Apparently, uranium-236 has weak spots. That's what I mean about those attractive forces that totally boggle my mind and I don't understand. The subatomic properties of uranium-236 means it almost always breaks in the same place. Not always, but almost. So the most common chunks, like the towers that used to break off, the most common chunks are molybdenum and tin. But, you know, it could be niobium or ruthenium or zirconium. You'll get a couple of other products. And from tin, you'll get a couple of other products. I hope everybody understands these are the most common or the average. But there are others. Are we clear with that? Like if I drop a Lego castle a million times, they'll be a little different, the pieces. Something else I want you to notice, though, and this is not a trivial issue. Look at molybdenum here, 103. Now look at molybdenum there, 96. You're supposed to notice that this has 7 extra neutrons. And that's why it has an asterisk, because this is highly radioactive. Like my boy with too many pieces, those are going to fall off. And if you look over here, tin says 131, but in nature, tin is 119. That's 12 extra neutrons. These radioactive decay products, also called spent fuel, they are heavy and unstable, also known as high-level radioactive waste. Here's a funny thing. Nuclear fuel is not that radioactive. Nuclear fuel